This video is a little bit of an introduction to the lab that you will be performing where you will be determining the KSP of calcium sulfate. So the purpose of this lab is to actually find the value of calcium sulfate's KSP. You can see here that this is the reaction that you will be putting in your rice table ultimately to figure out that KSP value. And this is just representing the calcium ion as it's dissolving in an equilibrium system into calcium plus 2 and sulfate minus 2. Right here is your KSP expression, where again you'll be using to calculate that value. So when we start this, the first step of this is to run our calcium sulfate through something called a column. This is a column. This is a smaller version of the different kinds of columns that you see around different universities. I did a lot of column chromatography in my biochemistry courses, and they were these huge 5-foot columns that they kept in cold rooms. So this is a microscale version of that, but the column itself is filled with this brown-looking substance that has the texture of kind of like sand, and that is called the resin. The resin is a bunch of little naturally negative charged pieces. So you've got all these little negative charged things in here, and we're going to talk about the chemistry behind it momentarily. But what I do want to talk about is the working of this column. The water level currently in this picture is up here, but what you're going to be doing is you're going to be pouring your sample into this, and you're going to open up the stopcock down here, and fluid will come out of the tip on the bottom. Currently, when the stopcock is parallel to the tip like it is, that means it's closed, and just like a burette tip, which you've used before and you're going to use again in this lab, when you turn it perpendicular up and down, that is when the tip will be open and fluid will run through. What I need to caution you about is when you are running fluid through and it's coming out here, this level starts to drop. You are never to let the water level drop into the resin. You never want there to be air pockets or dry resin in the experiment, because that could mess up the exchange of ions that I am about to explain. So what is column chromatography and how does it work? You're going to be pouring your calcium sulfate solution into the column. It is a colorless, not green, colorless solution, and you know it's got calcium plus 2 and sulfate minus 2 ions in it. This cation particular exchange is a cation exchange. There's anion and cation. We're doing cation. So all the little resin balls, the blue balls here that you see, are naturally negatively charged. So what Ms. Rozier and I do, we do something called shock the column. We shock the column with nitric acid. So every single one of these little resin particles is covered with H pluses. And it is on the surface of that resin that the exchange is going to happen. So as we pour in our calcium and sulfate ions, the sulfate ions are just going to stick. Boom, they're attracted to all these positive charges, and they're just going to get stuck in the resin. Then the calcium plus 2 ions are actually going to do an exchange with 2 positive H pluses and send the H pluses through and out the tip, and the calcium plus 2 will also stay. But what's important to know is that for every 1 calcium, we get 2 H pluses coming out the other side. From that point, we can quantitatively determine the moles of those H pluses, and then figure out the moles of calcium plus 2, because we know that 2-to-1 ratio. So that is the next part of the lab. Once we do the column, we will then quantitatively figure out through a titration how many H pluses came through. So let's talk about the start of the actual column work. So before you actually start doing your column work, we're going to have to check the pH of the column itself. So because we shocked the column, and remember all those resin balls have H pluses on their surfaces, we need to make sure that none of the H plus has leached into the matrix of the column, and when we open up that tip, we want to make sure there's no H pluses coming out just from the column itself, because if that happens, you're going to get a too high number of moles of H plus, which is going to translate to too much calcium plus 2 in your calculation. So we want to verify that the liquid going through is 100% neutral before we put in our sample. So what you're going to do is check the pH of the water coming out of the tip before you start. When you do that, you're going to just open up the stopcock, let a drop fall out onto the paper, and if it's red or any color, orange, red, somewhere in that range, it's acidic and you have to let your instructor know right away, and we'll come over and help you neutralize the column. If it's neutral, the paper will just look like it's wet and you won't get any pink or red at all. And that's where we want to start. From that point, you're going to take 5 mils of the calcium sulfate in a syringe, and you're going to drip, a mil at a time into the top of the column. You're going to have a beaker under here. You're going to open the stopcock, and you're going to start to run that 5 mils of calcium sulfate down into the resin, and then you're going to keep adding water, rinse water, to ensure that all 5 mils get into the beaker. And remember that exchange that's going on. For every calcium plus 2 that goes in, 2 hydrogens are going to come out. So now you're going to see part 2 of the lab, and you're going to start part 2 of the lab with a beaker that's going to have a little bit of liquid in it, because it was only 5 mils of your sample and about 10 or 15 mils of rinse. So you're not going to have a lot of substance in the beaker, and that's sometimes hard to do a titration with, because we're going to put a magnetic stir bar into your beaker, so we want to beef up the volume a little bit. So before you start your titration, you're going to go ahead and chunk in some extra water. So now we've got water in here with the original H pluses that came out of your column. It doesn't matter how much water you add. The fact that we used 5 mils of sample of the calcium sulfate is all we care about. That 5 mils of sample contributed the set amount of H+, so the additional water will not change that fact. So when you start your titration, we're actually going to have a magnetic stirrer here, excuse me, that's a hard word, and we're going to put a little stir bar in there, and it's going to stir the solution for you as you're titrating. So again, this only consists of the 5 mils of eluent, rinse water, and the additional water you put in to give it a little bit of oomph in its volume. You also need to add a few drops of phenolphthalein. That is crucial. Do not forget to add the indicator. In your burette, you're going to have your standard, I believe you're using 0.02 molar sodium hydroxide, and you're going to start with an initial reading. If you can get your burette to 0.00 mils, that's fine, because that will be your initial reading. But regardless, wherever that reading is, it doesn't really matter. As long as you record that initial volume, you are good to go. Just make sure it's within a first mil, because we don't know how many mils this titration will take. So I want you to have it as full as possible. So you're going to slowly do your titration. You're going to maybe add a half mil to 1 mil increments, a little bit at a time, until you start to see a little bit of pink flashes. As soon as you start seeing any pink at all in your sample, you need to slow down and go dropwise until you get a final pink color, which I'm going to show you on the next slide. Make sure you record your final reading when you've reached that equivalence point. And we consider this to be a neutralized solution because of the color change. Here are some examples. This is your starting liquid, will be clear. This is what a good equivalence point looks like, barely pink. If you go this dark, you overshot. So you want to take it slow. You're only going to get one shot at this, because we have to run the samples through the column before they can be titrated, and we only have one column per group. So you only get one shot. So slow is better. So you're going to titrate slowly, and then you want to get as light a pink. Don't come and ask us, is this too light? If it's a pink you can see, it's not too light. If it can't be seen, it's obviously not pink. If it's something that looks like this beautiful fuchsia, which is my favorite color, it is too dark and it is overshot. If it's overshot, you still take that data and work with it, but you're going to get data from other groups as well, and you'll be able to average it out. So what's important about this equivalence point? At the equivalence point, moles of acid equals moles of base. So whatever base volume you have, you'll be able to take that volume and the molarity of the base from the burette, that volume from the burette, to find moles of the base, which translates into the moles of H plus that you have in your sample. So from there, and I'm just going to talk you through the calculations, if you are doing the calcs at the end of the lab and are having trouble, you can come back to the video and look at this page, because this is going through all the calculations, probably in more detail than I should, but you're going to use the milliliters from the burette again, and you're going to multiply that in that volume in liters by the 0.02 molar sodium hydroxide to find the moles of sodium hydroxide. Because you found those moles at the equivalence point, we know that that then is equal to the moles of H plus. You're going to then go back to that whole concept of that 2 H pluses for every 1 calcium exchange. So if we know that we have X moles of H plus, we know that we have half as much of Ca plus 2, because for every 2 H pluses, there was 1 Ca plus 2. Once we know our moles of Ca plus 2, we can divide by the liters. Remember, we used 5 mils, so we're going to divide by 0.005 liters to find the molarity of Ca plus 2. That molarity of Ca plus 2 is your X here. You know that X is the concentration of Ca plus 2. And look here, it's also the concentration of the sulfate. So you'll be able to take those two molarities, multiply, and get your KSP. You're going to have your data, and then you're going to get data from 2 other teams, so you have 3 pieces of data to work with, and you're going to calculate 3 different Ks and find an average K. So I think that's pretty straightforward. Be sure to work on that pre-lab and have it done and ready to go before we do the actual lab itself, and we will see you guys in class.